Okay, so here's the question. We have a long coaxial cable has a uniform volume charge density rho on the inner cylinder of radius A and a uniform surface charge density on the outer cylinder radius B. And it just seems that the charge density is just enough so that it balances out the surface charge density on the internal one, the volume charge density on the internal one, so that the cable overall is electrically neutral. And the question is find E, the electric field everywhere in space, and sketch it. Okay, so why don't we begin with a simple sketch of this? Let's go to the pad. We're gonna start with a simple sketch of this. So we have two cylinders. Okay, and on this guy, there's a plus rho. And on this guy, there's a minus sigma, such that the entire thing is electrically neutral, which means there's no charge on the entire thing, or there's balanced charge. Okay, so, and we want the electric field everywhere. So what is E everywhere? Okay. And we know that the radius of the inner one is A. So from here to here is A. This is the center. From here to here is A. And the radius of the outer one, so like if this is the outer one, from here to here is B. Okay, well, let's do it first inside the inner cylinder. So what we're going to do, we're going to use Gauss's law. This is a straightforward application of Gauss's law, which says the closed integral of EDA equals Q enclosed inside a Gaussian surface divided by epsilon. And my Gaussian surface, of course, will consist of a small cylinder here inside with the radius R. So now I am working where R is less than A. So I'm working inside. Okay, well, so I need to find the charge enclosed. So Q, this is a uniform charge distribution, but even with that, I could still integrate. I could do Q enclosed is equal to rho g tau, and that's a volume integral. So I'm going to assume some knowledge here. I won't do it. This is over V, and in cylindrical coordinates, this is just turns out to be the volume of the cylinder, which is pi, or let's call it, since we're working cylindrical coordinates, let's do S here on this guy here. Step down. So let's do S. So this is just rho pi S squared times the length of the Gaussian surface that I chose. Okay, times the length of the Gaussian surface I chose, so that's my Q enclosed. And if I put this in Gauss's law, so I will get E times dA. Okay, so this we have here. The reason we could use Gauss's law is because we have symmetry. There's cylindrical symmetry, and so the sides don't contribute, but the surfaces of the cylinder do, and that enables me to take A outside the integral, so it becomes EdA, which just becomes Q enclosed over epsilon, which becomes EA, and the area of the cylinder is just 2 pi L times S, the radius S. So E 2 pi SL equals rho pi S squared L over epsilon. And as you can see, L cancels out. So this is independent of the length of the Gaussian surface that I take, as it should be. So E will equal to rho. 1s cancels out, so I get S over 2, the pi cancels out, and I get 2 epsilon. And of course this is again in the S direction. Okay, so that's inside the internal cylinder. Okay, so this is for this case here, R less than A. Now let's go in between them, in between the two cylinders. So so I have two cylinders. And so since I'm going to go in between them, my Gaussian surface will be here. And this is my S now. And this bad. Oh, gotta do something this bad. Keeps closing on me. Okay, sorry about that. Let me get the pad opened. Okay, it takes a few moments so it syncs, so I don't have to rewrite what I wrote. Give it a second. So now I'm going to take a Gaussian surface between both of my cylinders, so I can evaluate the electric field in the region in between them. Okay, here we go. Coming back. So this is my S now. And of course, this here is my A. And this here was my B. So now R. So now in this case, R. So this is the second case. This here was the first case. So now R is between A and B. Or S is in between A and B. This here was S. Okay, so again, Gauss's law, closed integral of EdA on the Gaussian surface is equal to Q enclosed over epsilon. In this case, so the surface charge of the outer cylinder is on the surface of the outer cylinder, which means there's nothing in between. However, my region, my Gaussian surface, is enclosing the entire internal cylinder, which means I will get the entire charge of the internal cylinder in my Q enclosed. And so Q enclosed will be the integral of rho d tau, but this time, so I should have been a little bit more explicit about this. Here, when I did my integral in cylindrical coordinates, I'm just assuming some calculus knowledge here, so I'm not doing this in depth, so I don't bore you. But I've integrated from 0 to s on the GS part. Here, I would have to integrate from 0 to a because I'm enclosing my entire inner cylinder, because the entire charge on the inner cylinder is actually in my Gaussian surface. So here, when I do the integral, I will get the entire volume of the inner cylinder, which will be pi a squared rho uniform pi a squared times L. This is L is the length of my Gaussian surface. So yeah, rho pi a squared L. And so now plug that in there, and again by symmetry I could pull that out. So times 2 pi s L equals rho pi a squared L. Again, L cancels, pi cancels, and I get my electric field to be rho a squared over 2 epsilon s in the region in between. And of course, again, this is the s direction. Put this in a nice box. So we're done with that. Now let's go over the third case. And in the third case, we're going to do outside. So that's R, S will be, so this case will be S greater than B, meaning outside both. So if this is my one of them, and this is the other one. Oops. No, I don't want that. Okay, whatever. So something like keeps. Okay, whatever. Okay, so now my Gaussian surface will be on the entire thing. So my S now goes from here to here. This is my S. Of course, this is my A. And this is my B. I'm not sure why I'm doing so much drawing, because this case is really simple and it's clear. Well, what is Q enclosed? A Q enclosed is actually 0 because it's electrically neutral. That's what the question originally said. So if I were to apply Gauss's law here, the electric field will just be 0 because EGA equals Q enclosed over epsilon, and Q enclosed equals 0. Neutral, which means E has to equal 0 in that region. Okay, and then we could sketch this. That's a simple task now that we have it. So let's say this is S and this is E. And we had the inner cylinder goes all the way to A. So let's say this is A here. Let's say that this is B here. And then S goes on. Now, when we were less than A, it was actually linear in S because rho over 2 epsilon is some number multiplied by S. So that's a straight line. And it's going to go something like this. Okay, going to go to 0 because when S is 0, E is 0. Okay, and then when we were between A and B, well, it turned out to be rho A squared over 2 epsilon. This whole thing is a number here. rho A squared over 2 epsilon 1 over S. Well, that's a hyperbola that looks something like this, because remember, this is the variable here. S is the variable. So as S increases, of course, this is in the denominator, the electric field will decrease in a hyperbolic way. So let's say it goes something like this to here, for example. And then all of a sudden it drops down to 0 when we are greater than B. So greater than B, it just goes to 0. So this is the sketch. That does it. Please don't forget to rate, comment, and subscribe if you want. Thank you.